In its February 2015 publication, the National Institute of Standards and Technology asserted, "A new economy built on the massive growth of endpoints on the Internet will require precise and verifiable timing in ways that current systems do not support." NIST went on to elaborate, applications, computers, and communications systems have been developed with modules and layers that optimize data processing but degrade accurate timing. Dr. Thomas Fenning of Microsoft Corporation offered, virtualization technology, processor performance, and networking complexity outpace deliverable accuracy in legacy time synchronization solutions. He continued, worldwide large-scale data centers and cloud-based IT solutions create new challenges for operators, developers, and customers to meet business and regulatory requirements for workloads demanding system clock accuracy and precision across geographic locations. In his discussion about the blockchain transaction order problem, Dr. Mark Russinovich, the CTO of Azure at Microsoft Corporation, explained how this new technology takes a dependency on UTC-accurate system clocks across the participating platforms. The transaction order problem challenge is agreeing on transaction order to prevent double spend. Ideal System uses a global timestamp to determine transaction order. Each timestamp includes the previous in its hash, forming a chain. But legacy time synchronization solutions are falling short. In their October 2015 publication, researchers at Boston University called out the risk of network attackers exploiting unauthenticated NTP traffic to alter the time on synchronizing client systems. Their research indicated that almost a third of the NTP time servers worldwide are lacking in both accuracy and trustworthiness. Ask Bjorn Hansen, the developer and maintainer of the crowdsourced NTP Pool project, put it, "If business, organization, or human life depends on having correct time or can be harmed by it being wrong, you shouldn't just get it off the internet." Volunteer-based resources such as the NTP Pool project and its no longer curated predecessor at ntp.org do not indemnify you when you rely on them for your computer system clock accuracy. Meanwhile, the stakes are getting higher. Financial services firms operate under the rules set by regulatory authorities. In the US, these rules are set and enforced by the Securities and Exchange Commission. Its counterpart in the EU is the European Securities and Markets Authority. Both authorities have enacted new rules requiring better clock accuracy in computers being used for delivering financial services. In the US, the Financial Industry Regulatory Authority has been working with its member firms to meet the new clock accuracy requirements enacted by the Securities and Exchange Commission in July of 2016. Under the rule, the tolerance for computer clocks must be reduced from 1 second to 50 milliseconds by February 20th, 2017. The European Securities and Markets Authority expects financial services firms to meet an even more stringent business clock accuracy requirement of 1 millisecond diverged from UTC. These requirements are applicable to computer systems that operate on-premises and in cloud space. Financial services and information technology are 2 of 16 infrastructure sectors that the U.S. Department of Homeland Security has deemed vital to national security. These assets, systems, and networks, whether physical or virtual, are considered so essential to the United States that their incapacitation or destruction would have a debilitating effect on national security, economic stability, public health, and safety. These critical infrastructure components have become interdependent across vast regions, crossing jurisdictional and national boundaries and time zones. The need for accurate and precise position, navigation, and timing services has become more crucial. This increased dependency on timing services has left these sectors vulnerable to disruption. The Department of Homeland Security is inviting public and industry collaboration to develop assured timing technology for critical infrastructure that could easily integrate into existing systems. The goal is to provide secure and thorough timing inputs for critical systems, and reliably detect timing errors or manipulation. These contemporary challenges have not been resolved for organizations that made Windows a foundation of their IT investment. Microsoft guidance continues to warn users that the Windows Time Service cannot reliably maintain sync time to the range of 1 to 2 seconds. Such tolerances are outside the design specification. This stance renders all third-party solutions currently relying on the Windows Time Service framework suspect. Positioning, navigation, and timing are 3 distinct capabilities. Each is a complex field by itself. Of these, timing is the ability to acquire and maintain accurate time compared to a standard, and to do so anywhere in the world within a user-defined precision range. The Coordinated Universal Time, or UTC, is the primary time standard used worldwide to regulate clocks and time. Sync and Scale collaborated with Microsoft Corporation and the NIST Time and Frequency Division to develop, calibrate, and validate an end-to-end timing solution for the Windows Server OS and hypervisor. This engineering collaboration is essential for delivering an enterprise-class solution across the complete stack of hardware, virtualization, OS, and application at data center scale. Sync and Scale became a member of the Microsoft Cloud and Enterprise Ecosystem Engineering Access Program in 2014. On that occasion, Mr. Chris Phillips, General Manager of the Partner and Customer Ecosystems organization at Microsoft, said, "Microsoft welcomes Sync and Scale as a hardware partner who is advancing the Windows Server platform in this technology space, completing our own engineering investments to meet customer computing needs spanning on-premises and cloud spaces in a cost-effective manner." Since then, Sync and Scale has expanded its relationship with Microsoft to become a member of its Enterprise Cloud Alliance. Sync and Scale recently entered the second year of a multi-year cooperative research and development agreement with the NIST Time and Frequency Division in Boulder, Colorado. This effort is for the development of a modern framework and associated methods and tools to calibrate, verify, and measure system clocks of independently operated servers and personal computers. It is jointly led by NIST Fellow Dr. Judah Levine and Mr. Sean Voba of Sync and Scale. NIST physicist Dr. Jeff Sherman explained the design of an early atomic clock to the Sync and Scale and Microsoft visitors in June 2016. Microsoft engineers met with Dr. Levine at his NIST Gila lab to discuss the measurement results of the Sync and Scale-enabled Windows Server 2016 Technical Preview No. 5 on a Dell PowerEdge R630 server. This week-long visit by a contingent of Microsoft and Sync and Scale engineering teams was hosted by the NIST Time and Frequency Division at its lab facilities in Boulder, Colorado. Sync and Scale had gone through 2 iterations of its hardware development cycles prior to the Microsoft co-engineering partnership. During Windows Server 2016 development, Microsoft deployed Sync and Scale-enabled servers in its data centers on Redmond campus. Windows Time Service development and test activities are conducted in the Mega Lab in Building 88. These UTC-accurate servers are serviced by a single GPS antenna. They are accessible to different Microsoft development teams and self-managed. A high-availability time service configuration and hypervisor platform have been operating in the iconic original Microsoft Data Center in Building 11 since early 2016. These Dell PowerEdge servers are running the latest in development Windows Server 2016 builds and managed professionally in an IT production environment for long-haul enterprise-wide testing. A pair of servers provide Windows Time Service for internal NTP time synchronization needs. The third system operates a variety of virtual machines running Windows and Linux guest operating systems for different timing-aware projects. This installation is serviced by 2 GPS antennas. They deliver GPS time and frequency signals to all servers in the ensemble. In each server, the Sync and Scale hardware interfaces cooperate in an active standby mode to ensure the GPS signals are not interrupted. What did we learn? We learned that a UTC-accurate computer system clock should be a fundamental platform feature, analogous to the processor, memory, storage, and networking elements. A system clock should be able to maintain its UTC accuracy continuously and independently from other OS subsystems. A computer system clock should remain accurate regardless of the applications, workloads, or roles being operated on the system. A UTC-accurate computer system clock should be a ubiquitous platform feature in all server designs. A system clock should not require expensive hardware, elaborate infrastructure deployment, or arcane operational knowledge of conflated functionalities in order to maintain its UTC accuracy. A UTC-accurate computer system clock should be an enterprise-grade platform feature in both physical and virtual machines. An enterprise-class computer system of any design and price point, high-end, mid-range, or low-end, should be able to operate with UTC-accurate system clock as a native OS platform or a hypervisor of virtual machines running different OSs.